Okay, yeah, we're starting. Well, I wouldn't really waste time going through everything. Yeah, so the limit problems on the quiz aren't relevant for us for the test, so I'd probably skip that. But yeah, like finding the equations of lines, so let's talk about the test. Of course, you'll find the equation of lines given some information. Also in word problem form. So remember when I did that hot dog stand example? So things like that, and being able to develop a function based on information given in a word problem. You should be able to set up an equation of a line to solve something. Solve polynomials in general, I guess. Like a quadratic, you know how to solve a quadratic, or to find the vertex. About how to find domains of functions. Functions themselves as well as composite functions. Right, those are the guys like f of g of x, g of f of x, f of x. Difference coefficient. Yeah, stuff like that. Think about covers it. Is there anything I'm forgetting? Oh yes, simplifying expressions. It's going to be important in the coming days, including rational expressions. Expressions involving logs and exponentials. Of course, solve log and exponential equations. So those would be like the highlights. So I'll ask you to solve a bunch of different kinds of equations, you know, like a quadratic or something with logs and exponentials. Give you expressions with logs and exponentials, and all you have to do is simplify them. Or rational expansion, or this is the ratio of polynomials where you try to factor things and cancel things and simplify. Compute the difference quotient, finding lines, domains, composition, that sort of thing. Just the kind of algebra things that we've been doing in class, basically. And the kinds of things I gave you in the review. So I won't deviate too much from that. So. Any questions? And of course, on a test, there is partial credit. I will give you space to show everything that you're doing, so you should actually write out everything that you're doing. Other questions?
Will
Yeah.
transformations be on the test?
Yeah, those will, which is a good thing. Good thing you're running graphic. So know how to draw basic graphs, which sometimes might involve a transformation, right? So if I see a graph from like y equals ln x plus 1, you should understand you just graph ln, you shift it up 1, things like that. Because we'll do curve sketching is what it's called, which is graphing in very minute detail. We'll do that, so you should know the basic graphs of things. Know how to graph quadratics, lines, be able to do this quickly. Any other questions? So I'll take more questions on that if you have questions from the review or anything at the end. Let's actually just move on. We're going to wrap up 2.3 and 2.4 by finishing our discussion on the second derivative. So last time we spoke about what's called concavity, which there are two types, concave up and concave down. Remember, these were just the shapes. Concave up means you're shaped up like a cup. Concave down means you're shaped down like a frown. It doesn't have to do with increasing or decreasing or anything like that. It has to do with how your graph is shaped while it's doing what it's doing. And so that was concavity. We did a bunch of diagrams where I was explaining to you what it might look like. So concave up means the tangent line is always below the curve at any point. And concave down means the tangent line is above the curve at any point. And yeah, so now I want to actually talk about the formulation. Notice that what we were watching here were tangent lines, right? Where their slope, the slope is what we're watching. So something for like concave up, you realize that the slope is actually increasing as you move from left to right. For concave down, your slope is decreasing as you move from left to right. So now we're going to talk about what that means and how we can find those. So of course we're going to recall something important. If I look at the rate of change of a function, it is just, how do we find the rate of change of a function? What does that mean?
F of b minus f of a over b minus a.
That's the average rate of change of a function, or rate of change in general. What is it?
The derivative.
The derivative. So the rate of change of a function is the derivative of the function. Similarly now, if we can describe concavity by what the slope is doing, it stands to reason that what we want to look at is the rate of change of the slope, or the derivative. Which, what do you think that would be? Well, it's the derivative of the derivative. This last notion is called the second derivative. Right? And yes, there are things like the third derivative and the fourth derivative and the fifth derivative. Not all functions you can keep differentiating, but a lot of them you can. Well, a lot of the ones that we do in elementary calculus course, you can. But yeah, there's something known as a second derivative. So for example, let's look at some notations. So if we look at like f prime of x, or look like y prime, or something like dy dx. These are commonly the first derivative. The second derivative is very similar. You do 2 notches instead of 1. It's called f double prime, is how we call it. Right, so the third derivative you call a triple prime and so on. Or you can have y double prime. Here it's d squared y, dx squared is the notation for it. We can talk about that notation separately. This is called the second derivative. Nothing fancy, it's just equals the derivative of the derivative. So you find the derivative is a function itself that tells you the slope at any point. If you differentiate that function, find the derivative of that, you say you've taken a second derivative. And what you're actually doing is finding the rate of change of the slope. This means if slope is increasing, what do you expect to, would you describe that in terms of derivatives? Yeah, well if you look at concave up, notice that the slope is getting bigger and bigger and bigger. Slope is increasing. This basically means you're concave up, but what does it mean in terms of derivatives? F double prime must be positive, right? The derivative of the derivative must be increasing, positive, right? If slope is decreasing, this means you're concave down, which means your second derivative should be negative at that point. Copy those down because I want to erase everything and say something else. So right now I'm just giving you the concept. As I said, we're going to return to this and really go in detail with it, but right now I just want to introduce you to the concepts that we're going to be using. Are we done? What does this all mean? For f of x, its behavior, and graph. We're going to sort of put all these concepts together and see what we can talk about the behavior of a function based on derivatives. So here we have a function. What it tells us about how it tells us. So let's look at that. Let's look at the original function, f of x. What does f of x tell us about? What does knowing f of x give us? What information can we obtain from f?
The y value.
The y values. In other words, this talks about the points on the graph itself. F of x gives corresponding y values. Right, so you know that if you're ever in a situation where you want to know about what the function itself is doing, what outputs it's giving you, f of x is the function you should be looking at, right? How it tells you, if y is equal to f of x, this means x comma y is on the graph. Example, if I know that f of 1 is equal to 2, this means 1 comma 2 is a point on the graph. Right? So that's how it tells you. You basically look at the notation and it will tell you about points on the function. That's what f of x does. Anytime you need to know what a function is doing, what output values it's giving you, look at f of x. Now let's go to f prime of x. What would f prime of x tell us about it?
The slope of the tangent line.
What else? In terms of behavior, something that you can say, oh, the function is doing this thing.
Oh, it's increasing or decreasing.
Right, it can tell you about increasing. Right, meaning if the function is going up, is it going from left to right? It can tell you about decreasing. If it's going down as you move from left to right. It can also tell you about maximums and minimums. Right? Basically, you know a max occurs when you're increasing, then you proceed decreasing, right? That will give you a max, right? Or if you're decreasing and then you proceed increasing, that will give you a min, right? And the slope, the derivative, can tell you about all that sort of information. How would it tell you? How would you know if something is increasing or decreasing? What would increasing mean?
That the slope's going up.
Which means?
Concave up.
No.
The derivative is
Derivative is?
Positive.
Positive. Derivative is positive, meaning increasing. What about decreasing? The derivative is negative, less than 0. There's also a notion about being horizontal or being flat. This is when your derivative is equal to 0, right? So this is like at the top of a shallow hill, where your tangent line is a horizontal line. That will give you something like the derivative is 0. Right? And then putting these together, if you know that you're increasing on the left, decreasing on the right, you're continuous the whole time, you must have passed through a maximum. If you're decreasing first, then you start increasing, and you're continuous the whole time, you must have hit a minimum, right? All this information you can tell from the first derivative. So the original function will tell you about points on the graph. It will tell you where the graph itself is at any given time. If you look at the first derivative, it means you want to figure out one of these 3 things, right? It means if you want to figure out one of these 3 things, you would never look at f. F is not the one to look at for that information. You want to find out about increasing, decreasing, maximums, or minimums, the first derivative is what you need to look at. You will not look at any other function other than the first derivative for this information. You would not look at any other function other than the original function for this information, right? Let's talk about the second derivative. What does the second derivative tell us about? Well, I sort of mentioned it before, concavity. Right? So it tells us about concave up. Up like a cup means how you're shaped. Concave down. Down like a frown. It also tells us about what we call inflection points. This happens when you switch concavity. So for example, something that looks like this, that point is called an inflection point. Or something that looks like that, that is called an inflection point. Notice on one side here, you're concave down, while on the other side there, you're concave up. So when your graph does this sort of inflection where it switches on you, that's called an inflection point, and the second derivative can tell you about that.
That concept is kind of the same as when you are, when the first derivative is no longer increasing, where it's 0, it means it's horizontal. When the second derivative is 0, we're at an inflection point.
It could be, yes. That would be the same thing, yes. It would hit 0 here in general. if it exists at all. But let's actually talk about that. How it tells us? Well, we know we're concave up if the second derivative is positive. Up, you're positive, you're feeling happy, you're smiling. We know you're concave down if your second derivative is negative. You're down, you're sad, you're negative, you're feeling unhappy, right? Inflection points this means you switch concavity. Right? So you have a point here where your f double prime is 0 or undefined, but definitely the function is continuous here. F continuous here. Right? But on the right side, you have your f double prime is positive, while over here you have your f double prime is negative. Once you switch this, the derivative switches sign, the second derivative, it means you hit an inflection point. It means like on one side you shape like a smiley face, but on the other side you shape like a frowning face, or vice versa. Right? It ends up being something like this happening. Right? Similarly here for max and min. Let's talk about max, and we'll come back to this. So again, here's a point where your first derivative is 0, or possibly undefined. It could be like a sharp corner. But definitely your function has to exist there. F is continuous there. But on one side, your derivative is increasing, so that's positive. But on the other side, your derivative is decreasing, so that's negative. And once your function actually exists here, it means you have to do something like that, which creates a maximum. Vice versa, you get a minimum. Right, so over here your f is decreasing, and over here your f is increasing. Over here your derivative is 0 or undefined, but f is continuous. And that creates a minimum, because you would have to do this, then that. So these functions, they all tell us something different about how a function behaves in general and its graph. The original function tells you about the corresponding y values, hence you can figure out coordinates. If you want to figure out a point on the graph, you always look at f of x itself. If you want to figure out about increasing, decreasing, maximum or minimum, you always look at the first derivative. You would not look at this or that if this is your goal. Similarly, if you want to find out about concavity or inflections, the second derivative is what you're looking at. You will not look at this or that. Right? So knowing what you need to look for, there's a different function that will give you that information. Any questions on this? Yeah.
Are there any other questions or ways that they could phrase the question for f double prime to cue us in that that's what the question is looking for? Or is the question going to be, what's the concavity of this curve? That seems right.
Yeah, well, when we go back to this stuff, there will be questions where they're like, oh, find the intervals of concavity, which means tell me the interval where it's concave up or concave down or something similar. But in general, you will be applying this in the context of something else. For example, if I want to graph a function and I want to know this what happens, you always find these pieces of information. Right? So you'll know you need to figure out where it's increasing, decreasing. You'll know you need to figure out where it's concave up, concave down in order to graph the picture. Right? So there are a lot of contexts where you need to know to do these. There are also a lot of things where they have this kind of interpretation, how the function, the derivative, and the second derivative relate to each other. For example, there was the application of, I spoke about this before, motion. Right? Where this was the position function, this was the velocity function, and this was the acceleration function. Right, so there are interpretations like that when you know you might need a second derivative or something else. So I know if I'm looking for acceleration, I look here and not there or there, right? And with these applications that we're using in class, I'll tell you at some point when you would do which one. But yeah, they always, the function is derivative and the second derivative, they always give you different kinds of information. Right? This mostly applies to the behavior of a function and its graph. This is the interpretation you'll give to the derivatives. Any other questions? All right, so write this down. Know this very well. Super important. the last Rich level table. We will come back to it, but it's important that you start getting comfortable what derivatives mean on their own. And yeah, like I said, you can have something like the third derivative, which in this class we'll never see an application of a third derivative really. If I'm asking, it's just as an exercise, give you something to do. But yeah, and in basic physics you'll never pass the second derivative either. In more advanced physics you'll use the third derivative a lot or something. Which, the third derivative, the technical term for that is called a jerk. So, if you see a geek, you know, one of those nerd jokes, like, you're a third derivative. It's like a nerd calling you a jerk. Just in case you saw a joke like that. I've seen one like that, and I was there snickering, no one else knew what was going on. But yeah, the second derivative, we won't go beyond that in this class. In terms of graphs and function behavior, these are what the meanings are. But again, the general interpretation for a derivative is the rate of change, how fast something is changing. So you can always think of the first derivative in any context as being how fast the function itself is changing at a certain point.
So is it like just as a jerk is like the change of acceleration?
Yeah, how fast is your acceleration changing? Yeah. Yeah, and that ends 2.3 and 2.4. The homework for that isn't due until after the first test, though. I want you guys to focus on the test for now. So after the test, the homework for those two sections are due. And so we will move on. 3.1. Derivative formulas. Recall f is a differentiable function. Then f prime of x is equal to what?
Limit as h equals to 0. F of x plus h minus f of x all over h.
All over h. That is the derivative. It is a limit. You'd have to plug this thing in, expand or whatever, try to figure out a way to cancel h so you can plug in h equals 0. This can be tedious. Right? You guys have done a quiz with limits on it. It's not a fun thing to do a limit sometimes. Right? And the question is there a shortcut? And of course, every time I ask a question like that, the answer is obviously yes. I wonder if there's a shortcut. Yes, there is. Let me answer that. Yes! Many of these limits are computed ahead of time. And made into formulas. So right now we're going to talk about derivative formulas. How to find a derivative without actually going through this tedious process. From this point on, well, you know, after the first test, you only do this process of finding a derivative if you're asked to do it, right? Otherwise, you'll just do it the short way. But yeah, usually there's going to be at least one problem on the test and the final where I'm going to ask you to do a derivative this way, but pretty much every other time I'm going to want you to do a shortcut because we don't have time for that. I ain't nobody got time for that. Okay. So let's talk about some general functions that are very common. Because I want to be able to actually differentiate something like x to the 20, but I don't want to be able to expand x plus 2 to the 20th power and then try to do that. Here's common functions. This one we mentioned before, constants. Right? So if I wanted to find the derivative with respect to x of a constant, not sure if I used that symbol before, but this is derivative with respect to x. That with respect to x just means I'm thinking of x as the independent variable of c. Okay? This we know was 0. I actually proved that for you guys. You plug this into the limit definition. Your f of x plus h and your f of x is just c itself, right? So you just have c minus c, you will always get 0, right? So this is actually a rule. I know that the derivative of a constant will always be 0. It doesn't matter what the constant is. So if I say, what's the derivative of 1? Well, the answer is 0. What's the derivative of 17? Well, the answer is 0. What's the derivative of pi? Well, the answer is 0. What's the derivative of e to the pi squared plus 3 to the second minus 4 over 1.2? Well, it's 0 because it's a constant. Derivative of any constant will always be 0. Alright, so this is the first rule. Let's start to make it a bit more general. Let's talk about the derivative. Let's talk about powers of x. Say n is a positive integer. And I want to find the derivative of x to the nth power. Well, how would we do that? Well, we start by taking that limit of f of x plus h, which is just going to be x plus h to the n minus x to the n all over h. Now there's something called the binomial formula, which we're going to use to expand that. If you don't remember what that is, I don't think you need to know it really. At least not beyond like a cube or something. And so you'd expand this, you get x to the n plus, you get n x to the n minus 1, x to the n minus 1 times h, plus you get n times n minus 1 over 2, x to the n minus 2 times h squared, blah, 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 blah. You end up with n, you end up with h to the n minus x to the n. Right, this is using the binomial formula. I'm sure you've seen it in algebra or something, but you don't really need to remember it here. Pascal's triangle. Okay. So when you do that, you plug that all in. What's going to happen is this is going to kill that guy. What's going to happen after that is you'd be able to factor out an h from everybody else. N x to the n minus 1, factor out an h, plus here I have n times n minus 1 over 2, x to the n minus 2 times h, blah, 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 blah. And I kill that h. Now when I plug in h equals 0, every single term except the first term is going to die. The result would be x n to the n minus 1. This gives us the rule for x to the n. This means the following. We have it differently. The derivative of x to the n is nx to the n minus 1. By the way, this also works for non-integers. To prove that, I need some more advanced derivative techniques, so we won't do that now, but notice that it also works for non-integers. This is a super important rule it is called the power rule. The power rule for derivatives. There's a power rule for integrals, which we'll get to the end of the semester, but this is called the power rule for derivatives, a very, very important rule. So examples here, if I ask you to differentiate x cubed 3x squared. You bring that power down, and then you subtract 1 from the power, right? So it would be 3x squared would be the answer. Which means if you went through this whole thing, at the end of the day, that's what you would have gotten, right? If I ask you what's the derivative of x to the 17, no one wants to expand x plus h to the 17th power. It's just going to be 17x to the 16. Which means if you plug that into this limit definition and went through the whole thing, you would have gotten that. What about the derivative of x itself, just derivative of x? What is that? 1. Because the power here is 1, you bring that down, and then you'd be left with x to the 0. X to the 0 is 1. So that's just 1. Something else that applies here that might not be obvious to you at first. Derivative of square root of x.
1 times x to the negative.
Right, you'd rewrite this as a power. This is just x to the 1/2 power, and then you apply that rule. You bring the power down, you subtract 1 from the power. 1/2 minus 1 is minus 1/2. So you can leave it as that, or you can rewrite this as 1 over 2 radical x. In general, I won't care about this. So yeah, in any case that you can write your function as something of that form, x to some constant power, this will be the derivative. So for example, what is the derivative of 1 over the cube root of x squared? Would you want to plug that into the limit definition? I wouldn't. Anyone knows how to conjugate a cube root? It's ugly. Not super ugly, but it's pretty ugly. Yeah, so how would you do that?
Could you rewrite the bottom?
As right, so here we do the flower power, right? Top is the flower, the bottom is the root. So this is really x to the 2/3. Then what?
X to the negative 2/3.
Right, you'd have to bring it up. Notice that your rule applies to things that look like x to the n, not things that look like 1 over x to the n. That 1 on the top is bad news. Right? One thing you're going to realize with rules, you have to apply them. They have to look like the form they are in the rule. So if there's anything off here, you can't do it. You have to rewrite it as much as possible to look like that. X to some power. So you're going to go x to the minus 2/3, what we learned from algebra. That's how you take a reciprocal. And now you can apply that rule. Bring this power down. Subtract 1 from the power. So that's minus 2/3 minus 1. What's minus 2/3 minus 1? Minus 5/3, right? That 1 you just write as 3/3, right? 1 you write as this denominator over itself. So it's minus 2 over 3, minus 3 over 3, you get minus 5 over 3. So that would be the answer. And we're big kids now, I really don't care if you write a negative power in your answer, it doesn't matter. In algebra, they're always like, don't leave negative powers in your answers. It's really no problem. Yeah, power rule, very important rule, remember that. It's just something that we know now. We just know this, like our names. You guys can go back and you can look at, we did some things over here, like an x squared or an x cubed. Oh, what's the derivative of x squared? Because we actually did that one. The long way.
2x.
Alright, derivative of x squared is going to be, bring that power down, 2, subtract 1 from the power, you get power 1, just 2x. You guys can look back at when we were doing the derivative of x squared using the limit definition. We also did the square root of x using the limit definition. You guys can look at it and compare it. I did this in like one step. Right? Which now, if anyone read ahead and knew things like this, when you were doing that quiz and I asked you, oh, do this derivative by taking the limit, you could have done the shortcut. Okay, you know I'm right. Okay, so yeah, that's called the power rule. Those are just some examples. Let's talk about exponentials. Now the proof for these are a little hairy, so I won't get into them. I don't particularly think there'll be any insight into it anyway. Let's talk about the ever important function, e to the x. What's the derivative of e to the x? Turns out to be itself. Right? Which is kind of why we like the number e. Right? When we make it into an exponential function, it is the only function other than 0 who is its own derivative. Right? No other function has that property. Right? E to the x is such a function that at every point its slope is the same as its current y value. Right? So it's always increasing by its own magnitude. It's really cool stuff. So that's e to the x. If you want things a bit more general, which I'll have to prove to you later, if necessary, a to the x in general, its derivative is a to the x times ln a. Notice that this also applies to e to the x, but ln e is just 1. Basically, the trick to figuring this out is to rewrite it as a base e. That's where the ln comes from. We'll talk about that later at some point. We can also find, believe it or not, the derivative of ln x. Does anyone know what that is? Derivative 1 over x. So your textbook probably has an incomplete discussion of why these things are true. They couldn't give you the real proof, so there's a lot of subtle things going on in the background. But yeah, something like this, you need to know. Derivative of ln x, you need to know. Derivative of this, you need to know. Right? So this pretty much applies to a being any constant, including e. Derivative of e to the x is e to the x. I don't really have to tell you anything about that, but if I said 2 to the x, what's that derivative? 2 to the x, ln 2. What if I said derivative of pi to the x? Panic.
Oh, it's the x ln.
Pi to the x times ln pi. It doesn't matter, it's just a constant. Right? Pi squared e to the x ln of pi squared e. Right? Doesn't matter once it's a constant. That's the rule. Doesn't matter how scary it looks, figure out when something is a constant versus a variable, and then find the rule that applies to that form. One thing I want you to emphasize here, note the difference between something like x to the n versus something like a to the x, or x to the or n to the x, right? Notice that here, the base is the variable, the power is the constant. Well, here it's the opposite. The base is constant. The power is variable. Right? They behave very differently. Right? So never mix those up. If you see like an x squared versus a 2 to the x, these are very different things, right? And different rules apply to them. The power rule applies here. The exponential rule applies here. What else did I want to tell you about this section? What about something like this? What's the answer?
Negative 2 to 3, negative 3.
Yep. Minus 2 over x cubed. I asked you to do that on the last quiz. You'll notice that when you're doing you had to do this. I'm sure it was a lot more annoying than it is here.
Can you explain that one, please?
Oh, I rewrote this as a power.
Oh, okay.
This is x to the minus 2.
Gotcha.
So remember at this point, so let's actually have a little discussion here. At this point, here's what we know. We're going to learn a lot more rules, but at this point, this is what we know. And we know derivative ln x is equal to x. Okay? So when you're faced with something like d dx of 1 over x squared, right? The first thing you have to figure out is what rule would apply, right? So you basically need to figure out, can I write this to look like one of those, right? That's the first thing you're going to start to think. Can I write this to look like a constant? No, it's not a constant, it has an x in it. So that's not going to work. Can I write it to look like an ln? No. How's an ln going to, where's the ln going to come from? That's not going to work. Can I write that to look like e to the x? That's definitely not an e to the x. The graphs are completely different, right? Can I write that to look like an a to the x? No. Here, the base needs to be constant. There needs to be a power, a variable in the power. Here, the only power I see is a 2, and that's a constant. It can't be that. Process of elimination means it has to be this guy, which means I have to be able to write this as that guy. So use my algebra, bring it up. To make the power negative, this rule doesn't care about the power being negative. The power just has to be constant. Doesn't matter if it's a positive or a negative constant. So then I just rewrite this to look like that. And then I can apply a rule. Yeah.
How is the derivative of e to the power of x is the same as e to the power of x?
Oh, well, I didn't show you the proof because it's kind of sketchy.
So it's just, there is no...
Right, there is a proof. I just show you wouldn't help.
Alright, I got you.
It's kind of something you take on faith. I mean, you can read it on your own, but I really don't. I'll just totally confuse all of you by showing you the proof. And not in a good way. It's the kind of thing if you were all math readers, I'd show you just to keep you up at night. But there's no point in torturing you guys like that. But yeah, at this point you take it, these 3 rules, take them on faith. Look them up on Google if you don't believe me. But those are the rules. And as you'll see here, at any given time, in the back of your mind, these rules have to be there. Because I'm going to give you a function, and it might look ugly and crazy, but at the end of the day, what you need to do is you need to finesse it to look like one of these rules to apply. So knowing the rules is the first step. You have to know these things. And all the other ones that I'm going to be giving you throughout this semester. Yes?
Isn't that also the quotient rule that could also apply to the 1
That's
over x?
3.3. Oh, that's 2 sections away. We'll get there. Here we're just noting some basic formulas. There are also some properties that are very important. And basically these properties arise from the fact that derivatives are limits. So anything we can do with limits, we can do with derivatives. For example, there's the constant factor property. This says the following. The derivative of a constant times a function is just the constant times the derivative of the function. In other words, we can factor constants out of a function when finding the derivative, and it won't affect anything. So an example here, I know how to find the derivative of, say, x cubed, but what if I needed to find the derivative of 5x cubed? Right? This 5 is a constant, right? X cubed is like, okay, I know the rule for that, it's the power rule, but now I multiply by a 5. How does that change everything? Turns out it just multiplies the whole answer by a 5. You can literally factor that 5 out and just differentiate the x cubed. The 5 just hangs around. So you'd have here that 5 times, apply the power rule here, it gives me what?
3x squared.
3x squared. Now I just multiply that 5 and that 3. And that would be the answer.
Couldn't you just save yourself time and
Multiply.
Yes.
bring the 3 down and just subtract 1?
Yeah. So I was going to mention that here. I wrote up, like, this is the very first time I'm telling you about this rule, so I deliberately wrote out the steps. So now what I'm going to mention is normally in everyday life, you literally jump from this step to that step. You'll see that you can bring the 3 down, this will become a 15 when you multiply, and then you subtract 1 from the power. So you don't have to show this, I showed it for deliberate effect. But yeah, in general, you just bring it down, multiply, subtract 1 from the power, you get to that one step. Right? I won't expect you to go through a bunch of steps to write that down. Especially since I'm never going to ask you to find the derivative of just one guy. You know, it's just going to be a bunch of stuff, and you don't want to waste time on one guy too much. Which brings us to the other rules. There is the sum difference property. This means if I take the derivative of the sum or the difference of two functions, then the answer is the derivative, the sum or difference of the original functions individually. This is called the sum difference rule. This works because I can literally, if there's a plus sign, I can literally break up a limit into a plus sign, right? The difference quotient is just a fraction. I can break a fraction into 2 parts across the numerator. So here, what we have is example. So now I can say something like y equals 3x to the 5th plus 2 radical x minus ln x, and I can say find y prime. So y prime equals power rule, and I apply the constant factor property. So I immediately get 15x to the 4 plus
2 radical x.
X to the negative 9.
Right, this guy here, you can even scribble it down just to make sure you can see it. That I'd rewrite as 2 to the 1/2. I'd bring the half down, multiply by 2, what would happen? It just becomes 1, and then I end up with x to the minus 1/2 minus
1 over x.
1 over x, right? So you see you're doing, I can give you a sum of things, you just concentrate individually. Yeah.
If the derivative of ln of x is just 1 over x, would it stand to reason to say that the derivative of ln of 2x is equal to 1 over 2x? Or how?
No. It turns out it's actually still 1 over x. We need to get to that. I need to talk about the chain rule before we do something fancy like that, which is 3.4. Now you're 3 seconds away. Okay, but so far we have rules like this. So they're the basic rules where like the power rule, the exponential rule, the rule for e to the x. But then I can actually combine these. If I multiply things by constants, it's okay. I can factor them out and just find the derivative of the function normally using one of the rules. If I have a sum of functions, several things added together or subtracting from each other, I can just, again, differentiate each term. Right? So now I know the basic rules for basic kinds of functions, but once I know that, I can take a bunch of functions together and find derivatives of it. And it's just a matter of looking at things in pieces. Is there anything else I wanted to understand? I wanted to get to the product and quotient rule today, but I think we'll move that off and I'll just do some more examples and then we can answer some problems from the review. And we'll do the product and the quotient rule next time. And the chain, we can do all that in one class. Find y prime if y is equal to work on so that's example 1, example 2. Example 1.
Y prime would equal 3 halves x to the negative 1 half plus, let's see, negative 3x to the power of negative 4 plus 2e to x.
Yeah. Basically, you rewrite this. This is 3x to the 1 half. This you can write as x to the minus 3, and that's just 2e to the x. Right? Power rule applies to these two. E to the x derivative, that is just itself. The constant doesn't affect anything. You just leave them there. Yeah, that's one step. What about this one though? Find the points where that guy has a horizontal tangent.
Alright, so
First of all, when do we have a horizontal tangent?
when y prime is equal to 0.
What did I call it y? Y prime equals 0. Right, where the derivative is 0, we get a horizontal tangent line, right? Because that means you're not changing, you're just flat. Okay, so the first thing we're going to do is we're going to find the derivative, we're going to say equal to 0. We're going to solve for it. How do we find the derivative? minus x. How do you know it's minus x?
The 2's gonna come down, so 2, it's gonna cancel just away.
Right. This guy here, that 2 on the bottom is really just a half. Right? I can factor out a half. Right? Realize in fractions you can slide things off as long as they stay in their relative positions. Right? So that 2 I can slide it off, just make sure it stays in the bottom. So really there's just a constant in front of this x squared, and I can apply the power rule. I'd end up with minus x. Derivative of minus x? Derivative of 7?
Nothing.
Right, because it's a constant. So that's my derivative for horizontal tangent line.
You would factor this thing and then set the 2 equals 0?
You need 6x squared minus x minus 1 equals 0. Can we factor that?
3x and 2x.
Just like a 3x and a 2x would work. The only way to get a 1 is a 1 and 1. What are the signs here? This would be a plus, that would be a minus, right? Because this would give me plus 2x. This would give me minus 3x. Product of the far terms and the near terms give you the middle term. So that's what we get, which means we have minus a third, or x can be a half. Right? In which case, you can find the corresponding y values. How would I find the y coordinates? Put it back here. The original. Remember when we're finding coordinates on a graph, we look at the original. So I'd have to plug it back here. So I'd have 2 times minus a third cubed minus a third squared over 2 minus become plus a third plus 7. For this one, you would have y equals 2 times a half cubed minus a half squared over 2 minus a half plus 7. Of course, ain't nobody got time for that. Call that A, call that B. And so the coordinates here are minus 1/3, comma A, and 1/2, comma B. Right, those just be numbers.
That was a lot of work.
What was a lot of work? This?
Yeah.
It's easy.
Luckily, I'm not a math.
Wait till we get this curve sketching. You're gonna love that.
Did we do that thing on the example? Where you plug in things?
Well, I wouldn't give you anything super annoying like that.
Thank God.
I'll give you something where the numbers work out nicely, usually. Yeah, so those are a couple examples. Let's do something that's more application-based, like a motion problem. And with this problem, we will end the section in 3.1.
No, because you said we still have chain, the other rules you have to show.
Yeah, those are in different sections. The quotient rule and the product rule are at 3.3, and the chain rule is at 3.4. It's a different section altogether.
So this means that 2.3, 2.4, and 3.1 will do one second.
After the test.
1 second.
Yeah. 3.1 you can probably give me on Thursday. It's a different era. We're all growing up.
No, we're not.
What? At time t equals 0, a diver jumps from a platform. Don't know why, he had his whole life ahead of him. There's a story here somewhere, but I don't think it's our concern. That is 32 feet above a pool. His position above the water is given by the following. It's given by this function. S of t equals minus 16t squared plus 16t plus 32, where t is time.
You could easily factor out a 16 from this.
Time in seconds. All right, so tell me how many seconds we are into his dive, and this function will give me his current position. Okay? And S is in feet. Okay, so here are some questions. When does the diver hit the water? What is the diver's velocity after 1 second? It's kind of like its speed, but you take direction into account. That actually wanted to be C. Just relabel that. B, I actually asked you to find the velocity function. Find the velocity function. D, what is the diver's impact velocity?
Meaning, how fast is the diver falling when he hits the water?
Yeah, at the moment he hits the water, what's the speed at impact?
Pretty hard.
It's hard. It's really,
No,
don't know if you'll survive.
his impact.
Find the diver's acceleration at time t. Tons of questions I can ask you about this. When is the diver traveling upwards or downwards?
Up when he jumps.
And when is his velocity 0? Okay. Now what? Start over here. A. When does he hit the water? No. What does hitting the water mean? How can you describe that?
The moment he connects with it.
The moment it connects with the water, what function would tell me about that?
Oh, the derivative, because then I
No,
already-
don't need derivative.
No?
Well-
Okay.
What's the interpretation of derivative? How fast something's moving. Did I ask you how fast something was moving?
That's
I
the
didn't.
velocity.
Yeah.
Would you set S of t equal to 0?
Yeah.
That's his position.
S of t is his position above the water. If he hits the water, what's his position? 0, right? So I need S itself to be 0. I need that entire function to be 0. So here we need position equals 0, which means I need the whole S of t, this whole thing, to be 0. Minus 16t squared plus 16t plus 32 equals 0. How do I solve that?
Factor it.
Yeah,
I'll take out 16.
you can take out a negative 16. I end up with t squared minus t
Minus 2.
minus 2.
And then t.
Does that factor? Does that foil nicely? Hopefully, it'll have to be a 1 and a 2 if it does. And I make it a minus 2 and a plus 1, right?
Yeah.
So either my t equals minus 1, which is rejected, because t is representing time. This is not quantum physics. So, which means t equals 2 is going to be the guy we're after. After t 2 seconds, he will hit the water.
It's going pretty quickly.
Yeah. Slippery slope has a hard life. So I decided to jump. I shouldn't have gotten rid of that, but whatever. No, someone wrote it down. A is gone. B. Find his velocity function.
Would you plug?
The
Prime.
second derivative.
No,
So, yeah,
that's a-
prime.
That's a 6
Velocity
Oh.
It's prime.
is the first derivative.
Yes.
If I v of t. Yeah, that one. We didn't talk about any other. Velocity is the rate of change of position. So this is just s prime of t, which is, now we know like shortcuts.
Negative
here it is.
32t.
That's a 16.
16.
Right? 32 is a constant. There isn't anything else. That was it. C. Find the velocity after 1 second. So 1 second into the dive, how fast is he moving? Plug in v of 1. Right? We want the velocity of that. So it's minus 32. 1 plus 16, which means minus 16. What does minus 16 mean?
He's falling at 16 feet per
Right,
second.
moving down. Right? There's a formulation in physics about direction in terms of up and down. Usually your positive means you're moving up, your negative means you're moving down. That's the difference between velocity and speed. Velocity carries information about your direction as well as how fast you're going. If you're in a 2D system like up or down or left or right, you can signify this by positive or negative. If you're in more than 2 dimensions, you use vectors. Moving on. D. What is his impact velocity? Nope.
I think, don't you plug into it? Isn't that what he is?
Plug in 2 where? Well, there are 2 keywords here, impact and velocity. So I know I'm looking at the velocity function, that much is clear, but impact.
Plug into the velocity.
Plug in 2 into the velocity. I know his impact happens at 2 seconds, and I want to know his velocity at that time. So here I want the velocity after 2 seconds. This means I'm just wanting v of 2. So I'm going to get minus 32 times 2 plus 16. What's that going to be?
It's negative 48 or something.
64.
Is it minus 48? Yeah,
Per second.
feet per second. That's really hard. So hard was the right answer. You're moving 48 feet a second. I'm pretty sure he died. This makes this a very tragic problem. 48 feet in a second? Are you kidding? You know how fast that is?
I mean, that's still well below terminal velocity.
What else do we have?
Now we take the second derivative, right?
Find the acceleration. Yes. So yeah, now this is the second derivative. We know the acceleration. This is called acceleration is a of t. You can think of it as the second derivative of position or the first derivative of velocity. They're the same. So the first derivative of this is just minus 32, which means the acceleration is always minus 32 down. Like that's actually gravity. That's the acceleration due to gravity. It's minus 32. So your acceleration is a constant function in this case.
Wait, how did you get negative 32?
Oh, I differentiated the velocity. Derivative of 16 is 0, derivative of t is 1, and that constant just times out by the constant factor rule. So it's just minus 32. When is he moving up or down?
Moving up or down?
No, like when, in general, when?
When you jump.
When is he moving up? How do we know he's going up? No? Position function is positive the whole time until he hits the water.
You can plug in something before one or like.
Oh, set the first derivative equal to 0 and yeah, something.
So you set v of t equal to 0, what would that give us?
A maximum,
How do you know it would be a maximum?
because that's when
Anyway,
the tangent
so
line
you-
would be a flat line.
So t would be what in this case? A half, right?
So
So what does that mean? How does that help?
That means from the start time to a half second later, that's the time when he's moving upwards. And then after,
So impact happens here, the jump happens here, and his velocity hits 0 around here. How do I know if he's moving up or down? Which part?
You plug in
Plug in numbers into what?
the original function. The derivative.
The derivative. Why would I plug it into the derivative?
Because you can see what the derivative is zero.
Because the whole derivative tells us if it's going up or down. We gotta see if it works.
Right. This is velocity. I know about moving up or down based on the sign of the velocity itself. So what I did was I figured out where the velocity is 0, and I want to figure out now where is it greater than 0 or less than 0, right? Moving up or down is a change in position. So it's not the original position, it's how it's changing. So what I do is I plug in a number here, like take t equals 0.25 or a quarter, right, into this, right? So here my velocity of a quarter is going to be minus 32 over 4 plus 16. What does that give me?
that's 8 plus negative 8 plus 16.
It gives me positive 8. So here it's positive, right? Over here, if I plug in something else like a 1, t equals 1, my velocity would give me minus 32 times 1 plus 16. That's actually negative. So here's where I'm moving up, here's where I'm moving down. And so I'm moving up when t is between 0 and a half, and I'm moving down when t is between a half and 2.
Are we done?
Almost. When is the velocity 0? Was the last question I believe, which we had to answer to. I had to answer that. G. When is velocity 0? Well, that just means minus 32t plus 16 equals 0, which means your t equals a half. So essentially what happens here, he jumps, he starts to move up, then he stops in the air for a split second and then starts to go down. Right? That's how you change direction.
It's a for when you plug in the number, you intuitively just put in like 24.
Yeah, it doesn't matter what number in this interval I plug in. I just want to plug in one that's nice. So 1/4 was a nice number. Okay, that's the end of that problem. So, questions from the review. Also, the timing. I don't know how you guys feel about tomorrow. I don't particularly care when we get the test this week. So we can do it tomorrow if you guys like, but we can also postpone it.
Oh my god. Wow, yes.
Just get it over with.
No, I'm just getting over it. How about one?
So the thing is, the last day to drop the class is July 7th. So we have like over 2 weeks for you to know if you're doing well or not. So even if they ended this week, it doesn't matter to me. Are there any questions that were bothering you guys from the review or any of the things I mentioned? We can take them now.
And the exam will be on 1.1 to 1.6, right?
Yep. Chapter 1.
Can we go over the rules for logs and ln's again?
How?
Like the thing is log of something is equal to this, or like e to the power of ln of blah blah blah. Sometimes just e.
I have a problem.
Okay, yeah, there were some problems like that. You have a problem like that?
Yeah.
Yeah. Okay.
So it's e to the 2 ln x plus 3 e to the ln 2x.
Yeah. And the problem was to what?
Sorry?
What was the problem?
Simplify it, yeah.
Where was this from?
From the final 2009, something like that. I don't know exactly. I just put them all together. Sorry.
It's hoping final, probably 2009, spring or fall.
Yeah.
Fall or spring. But yeah, and we want to simplify.
Yes.
Okay.
That was actually fall of 2010.
Fall 2010. Okay. So yeah, how would we simplify that?
You could write that in terms of log multiplication.
Yeah.
Or
The e and l. Yeah, you just move the 2.
So
It
two
doesn't
X.
cancel out because the 2 is here. So what do we do with that 2?
You can make it e ln x squared.
Right. It's already dropped down. We can put it back up.
And that would be e ln 2x cubed.
This is just nope. There's no room to move something from in front of a d. Only a log. So that we can't really rewrite. But at this point, the ln and the e are right beside each other. That's when they cancel. That's x squared. And here, ln and e are right beside each other. So that's just 3 times 2x. So this is x squared plus 6x.
Why are we making it look so hard? Scared.
So unless the e and the ln are next to each other,
They have to be right next to each other to do that. So if there's a 2 in the way, you got to get rid of it.
what rule did you use to move the 2 to the exponent?
Oh, that's a rule that says log of x to the n is n log x. That's a rule. It was like the second log rule.
Can you do another one like this?
Was there another problem?
Yeah, I don't know.
You can do spring of 2014. It's f of x equals ln. On top it's going to be, so it's x e 5x.
In the power
A
is
power of
5x?
5x, yes, over square root of x plus 1.
Yeah.
That's the whole thing?
Yes.
Yeah, looks scary. We have to simplify it, right? How would you simplify it?
And break it down.
I would do
2. So it would be ln of e 5x times x. So you make that x into a, well, no, actually, I don't know.
Wouldn't you
No, there's no
subtract
room
it?
to move that.
It's like subtract.
It's subtracting, right? You have ln of something over something. So we're thinking of ln of a over b. That's the first thing I'm going to see.
Yeah.
Which means, which gives us what?
ln a.
ln a minus ln b. So I'm going to take ln of x e to the 5x minus ln of the square root of x plus 1. But we can go further. What about this one?
take out the power.
Like x squared.
There's a multiplication here. So if we have ln of a times b, that's ln of a plus ln of b. And so this I can break it into 2. ln of x plus ln of e to the 5x minus this guy. What will we do here?
ln x plus 1 to the negative, no, to the 1.
Right. This guy here is just x plus 1 to the 1/2 power, and this rule says I can bring that power down in front. So we're done?
I think we could further break up the ln x plus 1.
You cancel the
You
e
can't.
and ln.
This one though, ln and e are right beside each other, they cancel. So it's ln x plus 5x minus 1/2 ln x plus 1. There's no rule to break up this log of a sum. So that's it. Other questions?
I have a question.
Mm-hmm.
It says, the question said, write an equation for a quadratic function with vertex -8, 2.
Vertex is -8, 2
That passes through the point 2, 4.
through 2, 4. So remember that if we want a quadratic. What you would use here is called the standard form. So this means that a quadratic looks like this in standard form, where h, k is the vertex. A is the coefficient that stretches it vertically, and if it's negative, it opens down. If it's positive, it opens up. So what we would do here is, I know that y is equal to, I can replace -8 with h. And k I can replace with 2. And so now since when x equals 2, y equals 4, that's a coordinate on the graph, I can plug those in at the same time to solve for the a. So this means that 4 is equal to a times 2 plus 8 squared plus 2. This means I can bring this 2 over. 8 plus 2 is 10. This means your a is equal to 2 over 10 squared, which is just 2 over 100, which is 1 over 50. So ultimately your y is 1 over 50 x plus 8 squared plus 2.
And you just leave the x plus 8 squared as is, you don't need to expand
That's
it.
fine. Yeah, unless you're asked for a specific form, I don't really care what formula it is.
Like put in like ask for H and K. Oh, no.
Yeah, the vertex. The vertex happens at h and k. And if I also know an x and a y, I can solve for the a, which is what I do. Other questions?
Okay, I have one.
Mm-hmm.
The limit as x approaches -2. So on the numerator you have 1 over x plus 1/2
1 over x plus 1/2,
over x cubed plus 8.
x cubed plus 8.
Yeah.
Okay? What do we do here?
Common LCD,
Okay.
2x. Right.
So you multiply top and bottom by 2x. Okay, so you have the limit x approaches -2 of multiply here. The x would cancel here, the 2 would cancel here. I pretty much get x plus 2 over 2x times x cubed plus 8. Now what? This is the guy we have to fix. Turns out we can factor it. There's something called the sum of two cubes formula. there's also the difference of 2 cubes.
But,
So it means that this I can factor as 8 is actually 2 cubed.
oh,
So I can factor this as x plus 2 times x squared minus 2x plus 4. X plus 2's would cancel. And left with 1 over 2x times x squared minus 2x plus 4. And at this point I can plug in minus 2. It's going to be minus 4 times minus 2 squared plus 4 plus 4. So that's 4 plus 4 is 4. 3 4 is 12. 4 times 12 is 48. So it's minus 1 over 48. Any other questions?
For word problems, are you gonna give these questions with like a problem which you asked?
So the word problems, I'll ask you questions like Jhevon's hot dog stand, or those questions where they were describing like a box. Oh, here's a box with a square base.
Oh, no, can you
No.
go?
Minus volume form.
Okay, so that's the problem. One of the questions was a semicircle and a rectangle, and it asked to express the area A of the window.
Oh, the Norman window it's called?
Yeah. Okay, so you memorize the question.
No, that's what those windows are called.
Okay.
It's called a Norman window. So it's like a window where there's like that semicircle on top of it.
Right. And the perimeter is 30 feet.
So the perimeter is 30.
feet. And the question is, express the area A of the window as function of the width x of the window.
As function of x. Okay, so the width of the window would be this, that's x. And what did they tell you about this rectangle here? Is it a square, or did they give you any other information?
That's all I wrote down.
Okay, so call that something else, like y is this distance, right? So what is the area here? Well, it's going to be the area of the rectangle plus the area of the semicircle, right? So you're just basically going to add them up. So we're going to start with the area is area of rectangle plus area of the semicircle. What's the area of the rectangle? That's just x times y.
Plus,
Plus, what's the area of the semicircle? Well, the whole width is x. That ends up being the diameter of this circle, right? Which means the radius would be x over 2. What's the area of a circle? Pi r squared. So it's pi times x over 2 squared, but I only have a semicircle, so I cut that in half. Now I want this as a function of x. This is a function of x, but there's a y here. How do I get rid of that y?
set all of this equal to y, and then substitute what you just rearranged back into this.
How do I know that this is y? Where is it? What information haven't we used? That's always a good thing to. The perimeter. Why would they tell us that? Maybe it would come in handy. What is the perimeter? Perimeter is the length around the edge, right? Length around edge.
2y plus 2y.
So this would be x plus y, so that's already x plus 2y. So I know that that's 30. So 30 is equal to x plus 2y plus, what's the length around here? Half the circumference. What's the circumference?
Pi d.
Pi d.
Right, or 2 pi, or pi d. Right, so it's pi d, which d is x, right? But I want half of that. In other words, I can now solve for y. So my y is going to be 30 minus x minus pi over 2x all over 2. and I can come back here and plug that in. So this is x times 30 minus x minus pi over 2x all over 2. So that's my area as a function of x.
Yeah, I need one more day for the exam.
So will something like this be?
Are you gonna put like one of those box questions on there?
Maybe like a box or a farmer's building a rectangular fence around his garden or some silliness like that.
Nothing like that.
Alright, well, I gave you the review. I could give you this exact question.
No, I know, I hate that conversation.
Alright, so when do we want to take the test?
That's using the least amount of something.
You tell me.
I know,
Okay.
but I forgot to respond last night.
Do you want to vote on the test? I'm not. I wouldn't grade it till the weekend anyway, so there's really no
Can
rush
we do
as
a
far as I'm
box
concerned.
question?
What about the box?
I have the best question.
So it'll be some like an open box. I can say a square base. I could say something like the length of the base is twice the width of the base, or something silly like that. I'll give you something about the base or the height, and find its area in terms of one side. So like a surface area in terms of one side of the base. So something like that. In which case you're like, okay, this is your box over here. Square base, it's an x and an x. So the height, something else, call it y or h, doesn't really matter. Oh, and we need some other information. So they could also tell you something like the volume equals 100 centimeters squared or something. Okay. So now you first talk about the area. So we know the area is just the sum of the areas of all the faces. So I know that the area is equal to this area of the first face, x times y. The back is the same thing. So it's 2x times y. The side would also be x times y. So this side is also x times y. We generally have 4 xy's. Then there's the area of the base, which is just x times x. It's x squared. The problem is to find the area in terms of the length of the base, which means the y is not the length of the base, so I have to get rid of the y. And whenever you're in that position, you look for what other information they would have given you, for example, volume. So to find the y, you go to volume. So I know that volume is equal to 100, which is equal to length times width times height. The length and the width are the same, that's just x, so it's x squared times the height, which is y. Which means my y is going to be 100 over x squared. And then I plug it back in. So then I get 4x times 100 over x squared plus x squared. This cancels into that. So I get 400 over x plus x squared. Being able to do this sort of manipulation will be very come in handy when we're doing optimization and things of that sort. Other questions?
Can we please take the test on Wednesday?
Who would prefer Wednesday? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yeah, that's more than half already. Okay, yeah, we can make it Wednesday. And the homework for the thing we finished today, still push that to after the test, so Thursday. So right now, just focus on 1 through 6 and the review I gave you on the website. So I will see you guys tomorrow.
same thing.